I'm going to multiply this probability by the winnings to calculate the utility of arriving at this particular node in the tree. Okay? So I'm going to say, where's my calculator? Not yet, but this is, utility theory and Bayes are kind of about that close together. So yeah, there's Bayes involved here, but I haven't started using Bayes' law yet. Bayes did a whole bunch of utility theory, so I am doing some of the stuff Bayes studied. If I take 1, 2, 3, 4, 5, 6, that's $1 million, divided by 10,000, this is the utility of getting to this particular node, meaning it's worth $100 to have a lottery ticket. Okay?
Wouldn't it be worth 10 because you'd also have to include the $10 per ticket in each case, and then it would be...
Well, in fact, it costs 10. It doesn't add 10. So the utility of not having a lottery ticket, it turns out, is $90. Because if you could somehow magically just be at this node right here, then, hey, it's worth $100 for you to magically get to that node. But the only path to get to that node is paying $10. And so by virtue of you have to cross down this branch, your utility is minus 10, and minus 10 plus 100 ends up being 90. So I claim the utility of living in a universe where there is a lottery with a 1 in 10,000 chance of winning that pays off $1 million that you can enter only once is $90. Okay? So the utility of life is $90, and there you go. In other words, this lottery is going to lose $90 on average per participant. Do you see why lotteries like this don't exist? Because people that run lotteries understand utility theory. And so you can be pretty darn safe just saying it's a lottery, forget about it. That's stupid. Because somebody has worked through the math, or else they're losing money. But if for some reason somebody really did present this game to you, should you participate? Oh, I didn't subtract that 1 penny. Dang it. The utility of being in this state is actually...
$99.99.
Well, I don't actually subtract 1 penny from it. It's not $99.99. I subtract 1 penny times the 9,999 out of 10,000 chances that I will lose that penny. So in fact, this should be 100 minus 9,999 out of 10,000 times 0.01 penny. And that'll come out to 99.99999 or something like that, which is pretty darn close to 100. Basically, that penny didn't really sway things very much because losing apparently doesn't matter that much in this case. And so the total utility here is darn close to $90 to play the lottery. Okay? If I were to ask on an example test, what is the utility of living in this universe, it would be $90. Well now, let's say you were in this situation. You magically appeared at this node where such a lottery exists. Which way should you go? Participate or don't?
Participate.
How do we know?
The higher utility because that.
Yeah, the utility of going this way is 0. The utility of going this way is almost 100. Just slightly shy of 100. And 100 is more than 0. Therefore, pick the better one. Okay? Notice that there's 2 different kinds of nodes that I've drawn here. This is a decision node. I've said you get to choose left or right. And this is a probabilistic node. I've said the universe gets to choose whether or not you win. Or the balls, the ping pong balls they draw, or whatever determines who wins the lottery. And so you can imagine a tree of decisions in which there's a whole bunch of decisions, and some of the decisions might be probabilistic, and some of the decisions might be decision-based, and you can still put them all together to compute which node of the tree you ultimately want to end up at, right? I don't know what colors here represent. They're just some different kinds of nodes. And now we can handle uncertainty. Well, remember how breadth first search is a tree? So is utility, computing the utility of different decisions. It's kind of the same thing. It's just which way should we go? And so it turns out that yes, we can reinvent breadth first search with utility just fine. Everything we've studied so far has been decision making. Which way should we go? Well, always go the one that's the best payoff or the lowest cost. Well, now imagine a whole bunch of branches that have payoff, but there's probabilities. Maybe we go this way, maybe we go that way. Now your branching factor is going to grow even faster because you've got uncertainty and decisions to make, but you can still navigate it just using this same principle. Do you see that? So what I want to impress upon you is that which I'm studying now, utility theory, is really not different. It's just a totally different perspective of the exact same problem of how do you make decisions. You find a path from where you are to where you want to be, whichever goal you evaluate to be the best, and then you follow the decisions that get you there. See that? Okay. So there's a concept that comes up with beliefs. So I'm going to say, in this class, beliefs are a probability distribution. Let's suppose we believe that vaccines cause autism with this much probability, and we believe vaccines don't cause autism with that much probability. Is that reasonable?
No.
Or should we say it's more like that? It probably is more. I mean, at this point, we have pretty much established that vaccines don't cause autism. Would it be wrong to just say, I know vaccines don't cause autism. I'm giving 0 probability to the possibility and 100% of my probability to vaccines don't cause autism. Yeah, I'm going to claim that you're not being data-driven if you're doing this. This is kind of what I was alluding to before with people getting dogmatic, and humans are severely vulnerable to it. I'm going to claim that we don't really know anything based on evidence, because evidence isn't a proof. It drives me nuts when people use the word proof and evidence interchangeably. What's a proof?
Formal or mathematical?
Yeah, a proof uses formal logic. Proofs always start with assumptions. And whatever you prove is no stronger than your assumptions. But a proof leaves no room for uncertainty. Evidence, on the other hand, establishes the confidence of something. It makes your probability grow in one area and diminish in another area. But it never wipes away all possibility, right? So we have a lot of evidence that vaccines do not cause autism. But some person said they do. That's evidence, isn't it? It's wimpy weak sauce evidence, and it turns out that person is exposed as a fraud. So it's really weak evidence, but there is some reason to believe vaccines could cause autism. Very little reason. But if we're being totally honest to the data, your probability distribution should look kind of more like that, I claim. Yeah, absolutely. So I guess if you like to be dogmatic and drive your beliefs to 100%, and then you do utility theory on should I get my vaccines or should I not get my vaccines, you're going to come up with a number. And if you have a probability distribution that just reflects, I'm 99.99% confident that vaccines don't cause autism, but maybe they do. This is being open-minded, right? And then you do utility theory. Something's going to happen in both cases. And in both cases, you're probably going to end up getting the vaccine. So in this case, maybe it doesn't matter because which way you go doesn't sway your ultimate decision-making ability. But the one over here will compute probabilities that are consistent with the universe. The one over here is swayed by this arbitrary decision you made to throw 100% of your confidence behind one hypothesis. Right? So do you see why I'm suggesting that keeping your hypotheses proportional to the evidence is the AI way? It's the Bayesian statistical way. It's the way that's going to lead to correct utility numbers when you're doing your computations. Okay? There is something that bothers people. There's something called cognitive dissonance. Have you ever heard of that? Cognitive dissonance occurs when you have two beliefs in your head that can't be resolved against each other, such as vaccines cause autism and vaccines don't cause autism. Can those hypotheses both be true at the same time? No. One way to get rid of cognitive dissonance is to just snap your beliefs to 100% certainty on it must be this is true. And in many ways, this is appealing. But this also causes cognitive dissonance. Why?
That are conflicting.
Yeah, then you end up with 100% beliefs on two things that conflict with each other. So what's the right solution to that? I don't know. I claim that a little bit of intellectual humility is the right answer, which is, hey, let's adjust our beliefs to follow the data such that when you see something that supports this, increase the belief a little bit. When you see something that supports that, increase the belief a little bit. But try to keep your beliefs in consistence with the evidence. And now, some people get all obsessed about what constitutes evidence. There's scientific evidence. There's types of evidence that are not empirical, right? I mean, if your brother got vaccines and then got autism, is that evidence? It's anecdotal. It's not reliable. But it should sway your mind a little bit, or else you're being dogmatic and closed-minded. And I'm trying to suggest that a little bit of allowing the data to influence your beliefs will result in probabilities that mirror the universe, and that enables you to do correct calculations, which at least allows you to come to rational decisions about what you do. Let's do another utility theory example and see if we can work through how this allows you to make rational decisions. Let's suppose you're drilling for oil. Your choices are you can drill. Your choices are don't drill. Okay? If you drill, it's going to cost you $10 million, right? Because drilling is expensive. But here's something interesting. If you drill, then there's some probability that you'll find oil. And if you find oil, you get plus $1 billion, right? And if you don't find oil, what do you get? $0, usually. Okay.
You get 1 fee.
But let's make it more complicated just for fun. Oops. What happened?
That's true. You could strike gold.
Okay. Well, let's suppose instead you don't know what the market's going to do. And let's suppose that depending on the market, there's some chance you'll get $1 billion. And there's some chance that that will invade the Middle East and oil will become worth more, and then you'll get $10 billion. And then if you do that, maybe at some point there's a decision you could make on whether or not to sabotage politics in the Middle East to encourage a war in the Middle East. And then we could get all kinds of political uprisings and dirtiness, and we could make this a very nasty tree. And even if you don't drill, there's some chance that oil will spontaneously pop out of the ground. So you might get $1 billion just by sitting there. Pretty unlikely, though. You'll probably get a 0. So what if we put a 0.001 chance there and a 0.999 chance on that one, and a 0.8 chance on this one, and a 0.2 chance on that one, because they have to sum to 1 or it wouldn't be a distribution. And let's suppose this one's a decision. We'll say decisions get a red line. Wait, what was this one? I can't remember.
That was you get oil or you know oil.
Oh, that's probabilistic too, isn't it? Let's say there's a 0.4 chance you get oil and a 0.6 chance that you don't get oil. And the only decision you get to make is this top one. You with me? How do you make that decision? Well, we need to start computing the utilities of the various nodes in this tree. So what's the utility of this node in that tree? It's going to be $1 billion times 0.8 plus $10 billion times 0.2. And whatever number that is, that's the utility of this node, right? Of being in that state. Well, if we take that utility times 0.4 plus 0.6 times 0, we get the utility of being in this state. You with me? Oh no, and subtract 10 million. Don't forget that. That was important. Okay. If we take $1 billion times 0.001, that's the utility of being in this state. And now, do you see that my decision is actually really, really simple? How do I make a decision even though there's all these complexities, all these things that could happen, all this different stuff, I kind of just did a uniform cost search of my entire space, didn't I? And now the decision comes down to this. Do I want this decision or that decision? And what's the answer? Whichever one has better utility, right? Whichever one has lower cost. And now you can make any decision in the world by systematically searching through the space.